Okay. So let's return to the statement. Yeah. So again, to everyone who was online and couldn't hear, we're just doing a reminder of the last proposition in the previous lecture. Yeah. So we have that if you look at this, and then it's going to be equal to 0 for some positive integer p. Okay. So we have this proposition. So of course we know for eigenvectors, this expression corresponds to the case when p is equal to 1. Okay. So here we get something slightly weaker. We only get that taken to some power p. We get that this is equal to 0. All right. So this motivates a notion of a generalized eigenvector, which is something weaker than an eigenvector, because this power enters into the expression. So let's make a definition to capture that. So definition. Assume we have T, a linear operator on V, okay, as usual, and assume that lambda is a scalar in F, okay? Then we're going to say that a vector V in the vector space V, which is non-zero, is called a generalized eigenvector as usual of T corresponding to the eigenvalue lambda if we have that the expression in the previous proposition is 0. So if we have that T minus lambda times the identity to some power p evaluated on V gives us 0. Okay. So almost the same thing as usual for eigenvectors, but p, the power, is now allowed to be any integer, not just 1. All right. So in this case, we say that the vector is a generalized eigenvector. And to show you a quick example, so remember we have considered a large matrix in the previous lecture. Well, not previous. Yeah, actually in the previous lecture, yeah. So let me return to this example for a second. I'm talking about this one, okay? So hopefully you still have it in your notes. Here on the slide, I drew a lot of things which we don't need currently, but in the notes, you can see it without all this extra stuff, okay? So if we return to this example again for a second, then what can we say about the generalized eigenvectors here, okay? So what we have is that in this example, each vector in beta, the canonical basis for this operator is a generalized eigenvector of T. Okay, so we have this, and if you look at the numeric values that we have calculated for that example, we see from the matrix that we have the vectors v1, v2, v3 correspond to the scalar 2, lambda equal to 2, right? v5 and v6 to lambda equal to 3, and v7, v8 to lambda equal to 0. Okay, so we have these values corresponding to the operator in that case. Okay, so these are called generalized eigenvectors. Now, by analogy with how we formed eigenspaces from eigenvectors, we're going to do the same and define generalized eigenspaces using this new notion of generalized eigenvector. Okay, this is going to be the next definition. So again, the only thing that's going to change is that we allow arbitrary powers of the expression we use to define eigenvector. Okay, so the situation is the same. Assume that T is a linear operator on V, as usual. Okay, lambda an eigenvalue of T. Then the generalized eigenspace of T corresponding to lambda is going to be the set of all vectors. And now we are going to denote it as K subscript lambda. So remember, for eigenvectors, we used E subscript lambda. In this case, we're going to use K, which is, another letter. Nothing too special about it. So K lambda is going to consist of all vectors X in V, such that if we look at this expression T minus lambda I, to some power P evaluated on X is 0. And so that this holds for X for some P, for some positive integer P, okay? So note that P can depend on X. So each X, like for one X, you might have that, for example, this holds with P equal to 10, for another, it holds with P equal to 50, yeah? Doesn't matter. So as long as there exists a P like this, which makes this 0, then we add X to this set K lambda, okay? So this is what is called the generalized eigenspace corresponding to lambda. In other words, K lambda consists of 0 and the generalized eigenvectors of T corresponding to lambda. Okay, so just like we did for eigenspaces, for the usual eigenspaces. Okay, so now let's try to connect it to our familiar notion of eigenspaces. Yeah. So this is going to be theorem 7.1. Okay, so assume that T is a linear operator on V, as usual. Lambda is scalar in F. Assume that this is an eigenvalue of T. Then we have the following two observations. So first of all, since we call K lambda a generalized eigenspace, we're going to show that indeed this name is suggestive because it actually contains the usual eigenspace corresponding to the same eigenvalue. So we have that K lambda is a T invariant subspace of V, and it contains E lambda. Okay. So each generalized eigenspace contains the corresponding usual eigenspace. And part B, so we have that for every distinct eigenvalues, mu and lambda, of T, we have that the restriction of the linear operator T minus mu I to the generalized eigenspace K lambda is 1-to-1. Okay, so it's injective. As long as, so if you restrict, if you take the operator and use the eigenvalue which is different from lambda, but you restrict to the generalized eigenspace corresponding to lambda, we get an injection in this case. Okay, so we have these two properties. Let's check them. So proof. Part A first. Okay. So first of all, okay, so there are several claims here, right? So we are saying that it is a subspace, it is T invariant, and it contains E lambda. We have to check each of these three things. Yeah. So part A, first let's check that K lambda is a subspace of V. Okay, so this is the first claim. So, well, how do we check it? As usual, we just have to check it's closed on addition and scalar multiplication, yeah? And contains 0. So we have that 0 is in K lambda, just by definition, right? If you look at this definition, plug in 0 obviously satisfies it because we have a linear map, right? I mean, this part is a linear map. So it is equal to 0 when X is equal to 0. Okay, so we have 0 is in it. Now let X be an arbitrary element of K lambda. Then by definition of K lambda, there exists some P, a positive integer, such that T minus lambda I to the power P evaluated on X is equal to 0, right? Oh, and just to make sure we're all on the same page. So here the power is the composition, right? So it means we are taking the composition of this linear operator, T minus lambda I with itself, P times. Yeah, it's composition. Okay, so we have that this is equal to 0, right? By definition, because x is an element of k lambda. So suppose now, well, and the same for y, yeah? So suppose I have two elements. Let me write it. Like we have x and I have y, both in lambda. And there's p, and similarly, I have a q for y, right? So such that t minus lambda I to the power q evaluated on y is equal to 0. Okay? So we have two elements. We have to show that their sum is also in k lambda. Okay? So we have that t minus lambda I to the power p plus q evaluated on the sum x plus y. Yeah. So the hope is that we're going to get 0 here. If we apply each of the maps enough times to the sum, we're going to get 0. So let's check it. Okay. So this is the same as t minus lambda I to the power p plus q evaluated on x plus t minus lambda I to the power p plus q evaluated on y. So this is just linearity of the map t minus lambda I to the power p plus q, right? Okay, but now this is the same thing as t minus lambda I to the power q evaluated on 0 plus t minus lambda I to the power p evaluated on 0. Okay, so how do we get it? Because what does it mean to take this to the power p plus q? So it means we first take this to the power q, apply it to x plus y, well, apply it to x, let's say, and then we have to apply it p more times, right, to the result. But the result for q, for p, sorry, on x is 0 by assumption for the choice of p. And similarly, we get that the result is 0 when we apply the q's power of the separator to y by the choice of q, okay? And but of course, these are still linear operators. So now if we apply them to 0, we just get 0. So we get 0 plus 0, so altogether 0, okay? And so this shows that x plus y is also an element of k lambda, right? Witnessed by the integer p plus q. Okay, so this shows that the space is closed under addition. Similarly for scalar multiplication. So I'm not going to write it down out fully, but similarly for scalar multiplication. Okay, you can check it yourself. Okay, so we have checked that this is a subspace. Now we need to check that it is T invariant. Okay, so the next claim is that k lambda is T invariant. Okay, again, we just pick a vector in the space. So x belongs to k lambda, such that we have t minus lambda I to the power p evaluated on x is equal to 0. Okay, so we know such a p exists, fix it. Now we want to apply t to it and check that this is still in k lambda, right? Okay, so we have that t minus lambda I to the power p evaluated on the vector t of x. Okay, this is the same as composing with t. And moreover, the order doesn't matter because t commutes with this operator. Okay, so we can write this as t. Let me write it like this: t composed with t minus lambda I to the power p evaluated on x. And to be more completely precise, this is the order of operations. Okay, so why do we have this again? So this is because t commutes with t minus lambda I, and hence with t minus lambda I to the power p, just by linearity, right? So by linearity. Okay. But look, now we are taking the composition in the opposite order. So if I apply first this expression to x, we're going to get 0. So we get t of 0, right? And this is, of course, 0 again, by linearity of t. So we have shown that the same p works for the vector t of x. So the conclusion is that T of X belongs to K lambda. Yeah. The commuting part okay? Just write it out and yeah, because T obviously commutes with itself and it commutes with the identity, right? And so we repeatedly use this this remark to get that it commutes with this whole expression. Okay. Invariance. Okay. What remains is to check that it contains E lambda. So this is the last point here. E lambda is a subset of K lambda. Right. Let's check this. So assume, well, it's obvious basically, yeah. Because if X belongs to E lambda, the eigenspace E lambda, by definition of eigenspaces, this means that T minus lambda I to the power P of X is equal to 0, simply with P equal to 1 by definition of eigenspaces. Yeah. So we see that indeed E lambda is a subset of K lambda. All right. This is part A, and we also have part B, remember? So let me slide back for a second. So part B says that if I take some other eigenvalue now, mu, and look at the same operator, T minus mu I now with respect to mu, and if I restrict it to K lambda, what we get is an injection or a one-to-one linear operator. In other words, we need to show that the null space of the restriction is 0, right? So this is part B. Okay. So we show that the null space of the linear operator T minus mu I restricted to the invariant subspace K lambda is 0. Okay. And note, by the way, that this makes sense because we have already checked that K lambda is T invariant. And of course, it's also invariant with respect to the identity operator, I, right? So then this means that K lambda is invariant with respect to this whole operator. So we have that K lambda is T minus mu I invariant. So it makes sense to talk about the restriction, right? Okay, so let's calculate the null space now. So assume we have a vector X, a vector in K lambda, okay? And assume that T minus mu I of X is equal to 0. So it's an element of the null space, okay? Our task is to show that then X is 0. Let's argue by contradiction. So towards a contradiction, assume that X is not 0. Okay. And let's see what happens. So if it's not 0, we can take P to be the smallest integer greater than 0, such that we have T minus lambda I to the power P of X is equal to 0. We know such a P exists because X is an element of K lambda. All right. Now let's see what we get from this. So then we have also, well, before I do that, let me define Y to be one less power of the operator. So we take T minus lambda I to the power P minus 1 of X. Okay, so just one less iteration. Yes, question? Let's take Y to be one less power of X. Okay, so then we have that if I apply T minus lambda I once again to Y, this is the same as applying it P times to X, right? So this is, we get this, and we know that this is 0, right? So what we get is that Y belongs to E lambda, right? We see that Y is an eigenvector corresponding to the eigenvalue lambda, because we have this, that T minus lambda I of Y is equal to 0. Okay, so we have Y as an element of E lambda. Let's see what else we have here. So we also have that T minus mu I applied to y can be written as t minus mu I applied to t minus lambda I to the power p minus 1, remember, by the choice of y, applied to x. Okay, but this again commutes, because t commutes with itself and it commutes with the identity operator. So if we open the brackets and change the order, we get that this is the same as t minus lambda I to the power p minus 1 composed with t minus mu I applied to x. But now look, here we have that this is 0. And this map is linear as a composition of linear maps, right? So we apply a linear map to 0, but then this is just 0 as well. So we get that y belongs also to the eigenspace in mu. Okay, so we have y belongs to 2 eigenspaces, but this is unlikely, right? So from this we can conclude, well, because we know that if you intersect 2 eigenspaces corresponding to distinct eigenvalues, we only get the 0 vector, right? Okay, so we get 0, and y belongs to both of them, so y has to be 0 as well. So y is equal to 0. Okay, and we have y is equal to 0, but this contradicts the choice of p. Contradicting minimality of p. Because remember, p was chosen to be the smallest positive integer, so that the p's power of t minus lambda I evaluated on y gives us 0. But here we have found a smaller power, so this contradicts minimality of p. Okay, so we got a contradiction. We got a contradiction from assuming that x was not 0. So it means x is 0. Yeah. So x is equal to 0. X is equal to 0, and x was an arbitrary vector in the null space of the restriction of the operator, right? So this means we have demonstrated that t minus mu I restricted to k lambda is one-to-one or injective. Yeah, question? I'm sorry, I can't hear. If it is, yeah, but that's just a general fact, right? On a finite dimensional space, if you have a linear operator from the space into itself, then it's also a bidirectional. Yeah. Right. Okay. So we get, so we have proved the proposition. Okay. So or theorem rather. Okay. So we have this new spaces k lambda. So let's try to understand them further and try to develop a theory which is analogous to various results we had about the usual eigenspaces. So what we are trying to do next is to generalize some of the results we know for eigenspaces to generalized eigenspaces. Yeah? I mean, they're generalized, so we generalize. I guess. Okay. So the first thing we would like to do is to see if somehow we can split again the space into a direct sum with respect to those under some conditions. Okay. So we start with the following theorem, and this is theorem 7.3. Okay, so we're in the same situation as always. T is a linear operator in the vector space, finite dimensional. And we assume that the characteristic polynomial of T splits. Okay. So splits over the field of scalars F of our vector space in the usual sense. Yeah. So then let lambda 1 through lambda k list the distinct eigenvalues of T. Okay. Then for every vector x and v, there exist vectors vi belonging to the corresponding generalized eigenspace k lambda I. So for all I between 1 and k, such that x is the sum of them. So x is equal to v1 plus v2, etc., plus vk. Okay? So every vector can be written as a sum of vectors from the corresponding eigenspaces. So in other words, we are showing that the whole space is the sum of the generalized eigenspaces corresponding to the distinct eigenvalues. Yeah. But look, the assumption here is weaker than we did in the case of eigenvectors. So there, remember, we assumed diagonalizability of the operator, let's say. Now we're just assuming that the characteristic polynomial splits at the price of using generalized eigenspaces instead of the usual eigenspaces. Yeah, so it's a more general version of the result we already have seen. All right, so let's demonstrate this. So proof. Okay, so we're going to argue by induction on K the number of distinct eigenvalues of T. Eigenvalues of T. So first, the base case, k equals 1. Yeah. So in this case, we can let M be the multiplicity of the eigenvalue lambda 1, because we just have one eigenvalue in this case. Yeah. Okay, but then we have that lambda 1 minus t to the power m is the characteristic polynomial of t, right? Because m is the multiplicity. Remember, multiplicity is the power with which the monomial lambda 1 minus t appears in the splitting of the polynomial. Yeah. So we have that this is the characteristic polynomials of this simple form in this case. Okay. Yeah. So it just looks like this. Okay. So, but then we can write by the Cayley-Hamilton theorem. Let's plug t into this. Yeah. So we know that lambda 1 minus t to the power m is equal to t0. Well, it applies to t. Okay, so I need to evaluate this polynomial on t. So that is, we have that lambda 1 minus t to the power m is equal to t0, right? By Cayley-Hamilton. So maybe you thought you'll never see this again, this theorem, but no, it's actually useful. So by Cayley-Hamilton. All right, so we get this equality. So it follows. Okay, let me switch to the new page here, and let me copy this. So we have lambda 1 minus t to the power m is equal to 0, the 0 operator. Yeah. Okay, but then it follows that we have v is equal to k lambda 1. Right? Because no matter what vector I take here, if I plug it here, and this is going to play the role of p. So this m plays the role of p in the definition of k lambda, right? So we get that for any vector, this power gives me 0. So it means that every vector in V is in k lambda 1. Okay, so this proves the result in the case k equals to 1. So now let's do the inductive step. So k, we assume that k is greater than 1. And we assume that the result holds for less than k distinct eigenvalues. Right? So we're going to do the inductive step. All right. So suppose T has k distinct eigenvalues. Okay, and we're trying to show that the whole space is the sum of the generalized eigenspaces. Okay, so let M be the multiplicity of the last one, so of lambda k, and let us write f of t for the characteristic polynomial of the operator t. Okay, so we have the characteristic polynomial of t. Then we can write that f of t is equal to t minus lambda k to the power m times g of t for some polynomial t. Yeah, because m is the multiplicity of lambda k. So for some polynomial g of t, which is not divisible by t minus lambda k. Yeah, because m is the maximal power with which t minus lambda k appears in the splitting of the polynomial. Okay, so we have a presentation like this, and we try to utilize the inductive assumption. Okay, so for this we let W be the range of t minus lambda k times the identity to the power m. Okay, so this is a linear operator on V, and we look at the range of it and let W be the range of this operator. Okay, so the hope is that we'll be able to use the inductive assumption to W. So we need to check that we have smaller dimension here, etc. Okay, so first of all, we have that W is t invariant. Okay, let's check that W is t invariant. Well, take a vector x in W. So this is equivalent to their existing y in V, such that if I apply the linear operator to y, I get x, right? So such that t minus lambda k I to the power m applied to y gives me x, right? Just by definition of what range means. Okay, but then this means that t of x, and now I have to apply t to this again. So this is t composed with t minus lambda k I to the power m evaluated on y. And this is t minus lambda k I to the power m. Now I apply t to y. So again, we just use that t commutes with itself as always, and with the identity operator. So here we use that this and this, they commute by linearity of t. Okay, so since they commute, we can take the composition in the opposite order. But now if I look at t of y, this is an element of V, of course, yeah, just a vector in V. So what we get is that t of x, so we have here t of x is given by this, right? So this means that t of x is an element of the range of t minus lambda k I to the power m. Because we demonstrated that x can be written as applying this operator to some vector. Yeah, we don't care which one, just some vector. So it means it's in the range. All right. So this shows that W is t invariant. Indeed, yeah. We need to collect some more information about this subspace W before we can use, well, we need to check everything so that we can use the inductive assumption. So the first claim that we have here, claim 1, is that t minus lambda k I to the power m, this linear operator maps k lambda I onto itself for all I less than k. Okay. So if I look at any of the generalized eigenspaces k lambda I, and I take the image or the range of the operator applied to that subspace, we get all of that subspace back from this. Yeah? We get all of k lambda I. So let's check this claim. So proof of the claim. Indeed, if I take a vector, well, first of all, suppose let's fix I less than k. Yeah. And then we know that k lambda I is T invariant. This we already know from the previous theorem, that all of the generalized eigenspaces are T invariant. Okay. So this means that also k lambda I is T minus lambda k I to the power m invariant. Okay. Because if it's T invariant, and here we have something which is built as from T and from the identity linear operator. So it remains invariant with respect to this more complicated operator, right? So in other words, we get that T minus lambda k I to the power m maps k lambda I into itself. Okay, so not the difference between onto and into. Into means any vector from the subspace is mapped to a vector in the subspace. Onto means that every vector in the subspace can be obtained from some vector in that subspace by applying the operator. Yeah. Okay. So we have that this maps k lambda I into itself. Okay. And we also have that the subspace k lambda I, oops, excuse me, the eigenvalues are distinct, remember. So we have lambda k is not equal to lambda I. So we get that T minus lambda k I restricted to k lambda I is 1-to-1 by the previous theorem. So by theorem 7-1b, excuse me. Yeah, because remember there we had, if we have two distinct eigenvalues, then restricting the operator corresponding to one of them to the subspace corresponding to the other one is 1-to-1. Yeah. So we have this. So it's 1-to-1. Hence, it is onto. Actually, that was the remark earlier. Yeah, that it's finite dimensional. So it's onto. But then we have that T minus lambda k I to the power m restricted to the subspace k lambda I is also onto. Yeah, because if some operator is onto and I take some power of that operator, so just apply it repeatedly, I still get onto. Is this okay with everyone at this point? Yeah. Okay, so we see that the power to the power 1 is onto, and then we just take some power of it. So it's still going to be onto automatically. All right, so this shows that this operator is onto. All right. So this proves claim 1. And we have that claim 1 implies that for I less than k, k lambda I is contained in W. Okay. So again, let's look at it for a second. So this maps k lambda I onto itself. Okay. But remember, W is the range of this linear operator. So the conclusion by combining these two things is that k lambda is contained in W. Yeah, because k lambda is its own range. So it's contained in the range of the whole space. Yeah. Okay. So we have k lambda is contained in W. And hence, we have that lambda I is an eigenvalue of TW for all I less than k. All right. So bear with me. This is there are several steps in this proof, but so far, where are we so far? So we have defined this W to be the range of the whole space with respect to the operator given by some power of this. Okay. Now we have demonstrated that this operator maps k lambda I onto itself for each I below k. For each I below k, which then tells us that k lambda I is contained in W. Okay, and so from this we see that lambda I is an eigenvalue of TW for all I less than k. All right. So we're getting there. So we need one more claim, claim 2, which tells us that lambda k is not an eigenvalue of TW. Okay. So let's try to understand why this is the case. Lambda k is not an eigenvalue of TW. Proof of claim 2. So suppose it was, so suppose T of V is equal to lambda kv for some vector V in W. Yeah, that's what would it mean for it to be an eigenvalue. Okay, so suppose this happens towards a contradiction. But then we have that V is in W. By definition of W, this happens if and only if there exists Y in V, such that V is equal to T minus lambda K I to the power M applied to Y. Right? Because simply W is the range of the whole space with respect to this operator. Yeah, so it means there must exist some Y like this. All right. So we have that 0 is equal to T minus lambda K I applied to V, right? Because again, this is how V was chosen. Yeah, so we get that this is equal to 0. And so this also holds for the power. So we have T minus lambda K I to the power M plus 1 of Y. Yeah, we can alternatively write it like this. And we get that this is still equal to 0. All right. So then this implies that Y belongs to K lambda K. Yeah, because we can take P to be this M plus 1. So this P equal to M plus 1 witnesses that Y is an element of K lambda K. Okay. But by theorem 7-2b, this implies that V equals to T minus lambda K I M of Y is equal to 0. Okay, so we get that V is not an eigenvalue of TW. Okay, so so this concludes the proof of claim 2. Sorry, not eigenvalue, it makes no sense. Eigenvector, yeah? What I mean to say is eigenvector, not an eigenvector of TW. Okay, so this gives us claim 2. Okay, so let's regroup and let's see where we are so far. So claim 2 and claim 1. So now we have that since every eigenvalue of TW is also an eigenvalue of T, of course, yeah, because TW is just the restriction, we conclude that the distinct eigenvalues of TW are lambda 1 through lambda K minus 1. Okay, because we have demonstrated, so remember lambda 1 through lambda K listed all eigenvalues of T, right? And each eigenvalue of TW is in particular an eigenvalue of T. So it means that all eigenvalues of TW must appear in this list, lambda 1 through lambda K. And we have just ruled out the last one, lambda K. All right? And in claim 1, we have demonstrated that all the lambda I for I less than K are eigenvalues. So the conclusion of these two claims is that we have determined the eigenvalues of TW. And they are precisely lambda 1 through lambda K minus 1. Okay, so one less. So this means that W, the operator TW, has K minus 1 distinct eigenvalues. Yeah? So this puts us in a situation where we can apply the inductive assumption. but I don't think we have enough time to actually do the full argument. So I think I'll stop here. But okay, this is so. Remember what we achieved. So what we achieved is we found a subspace W of the space V, so that the restriction of the operator to it has k-1 eigenvalue. So it means inductive assumption can be applied to it now. Yeah. So we'll show that each vector in W can be written as a sum of the generalized eigenspaces as vectors, as a sum of vectors from the generalized eigenspaces for TW. And after that, we have to show that the whole space V can be written as a sum of W plus something, okay, plus another generalized eigenspace of T. Okay, but at least now we can apply the inductive assumption to TW. But we'll finish this part next time. Okay, I think it's a logical place, good logical place to stop here. Yeah. So thanks everyone. I'll stop here. Yeah. Thanks for coming.